Let us now try to write the VHDL code for a ripple carry adder. We have already seen what a ripple carry adder is in our previous videos. Now here we want to write a structural based VHDL code. Structural based VHDL code is basically function calls. It's very analogous to function calls in your C, C++, or Python programming. The best way to visualize a structural code can be something like this. So for the ripple carry adder, you have this block, which is the ripple carry adder. The ripple carry adder has two inputs, A and B. A is 4 bits and B is 4 bits wide. And it has one output, which is 4 bits wide. So this is the interface. Within this interface, you have a bunch of full adders and half adders. In structural programming, we refer to these as components. The basic idea of structural programming is that you first construct the components and then you interconnect the components. So construct the components. Step 2 is call the components. And third step is interconnect them. This is the idea of structural VHDL. Some of them call it functional VHDL. Some of them call it structural VHDL. Either way, you can use either of the terms. So let's look into how to build a structural VHDL code. You know that we have two components here. We have the half adder and the full adder. So first, we are going to write the logic for a half adder. So create a new VHDL file and save it as ha.vhd. Within this VHDL file, you have to write the following code. Entity half adder is, you know that a half adder has two inputs, X and Y. It has two outputs, the sum and the carry out, which are 1 bit wide. And then you end the entity. The next step is you write the architecture. So architecture arch of half adder is begin. I'm going to give the equations directly. So sum output is X XOR Y. And the carry out is X and Y. So this is the entity and architecture of the half adder, and make sure that you put it in a separate file called ha.vhd. Next, create another VHDL file and name it as fulladder.vhd. And within this file, we are going to write the logic for full adder. Entity full adder is, remember the full adder has three inputs, X, Y, and Z in std_logic. And it has two outputs, the sum and carry out, which are 1 bit wide. And end the entity. Next, we have to write the architecture. Arch of full adder is begin So the sum output is given as x XOR y XOR z, and the carry out is given by x and y or z and x XOR y and architecture. So we first constructed the components, and what I want you to do is, once you finish writing the half-adder.vhd, make sure you thoroughly test it on model sim. Once you test that, write the full adder component, test that thoroughly on model sim to make sure that the equations are right. Once you're done with that, we can go with the main entity file. So for the main entity file, you need to remember that the circuit is RCA. So we name the file as rca.vhd. Next we have entity. RCA is port. It has two inputs. So look at the interface. It has two inputs, A and B. A is 4 bits wide and B is 4 bits wide, and it has one output, S, which is 4 bits wide. So let's see how to write the ports. We write A comma B standard logic underscore vector. Since it is 4 bits, we write 3 down to 0. Similarly, your output S is again, this should be in standard logic vector 3 down to 0. S is out standard logic vector 3 down to 0. End entity. Remember, the problems that you have done until now, you just use standard logic because they were of the size 1, which means that they were only capable of holding 1 bit of information. Now here A and B are vectors which are of size 4, indicated by 3 down to 0. So you have A3, A2, A1, and A0. So this is your MSB and this is your LSB. Let's now write the architecture for the ripple carry adder. So we have architecture arch of RCA is. So to start off with structural programming, we first have to declare the components. To declare the components, all you have to do is copy the entity of the full adder and the half adder and put it down here. Essentially, we copy this one and we copy this one, with the only change that the entity is changed to component. So this and this are changed to component, and then you have end component over here and here. So copy paste and write it as component half adder is port X comma Y in standard logic, S comma C out standard logic, and end component. Similarly, put down the full adder. So component full adder is port X comma Y comma Z in standard logic, S comma C out standard logic, end component. Next, we are we're going to declare some signals that we need in our design. I'm going to put them down as and when needed. And all the signals, I'm going to write it as standard logic. Then I have my begin. If you look at the circuit diagram, the first component that we are using is a half adder. It has two inputs, A0 and B0, and it has two outputs, S0 and C1. So to call the half adder, we first give it a tag. Let's say half adder 0. This tag can be anything. You can abbreviate half adder. Just make sure that it is a single word. Half adder 0, the name of the component, which is half adder, the keyword, port and map. And within the port map, we have to specify the inputs and the outputs. And if you look at the half adder, the first two parameters are the inputs and the second two parameters are the outputs. Therefore, the inputs to the half adder are A0, B0, with the first output as a sum output indicated by this one, that is S0, and then we have a carry out, which is C1, semicolon. Now C1 is a signal, so I put it as a signal here. Let's go for the next component. Our next component is a full adder. It has three inputs, A1, B1, and the signal that was created before, C1, which was the carry out of the half adder. And it has two outputs, S1 and C2. So if you look at the full adder, the first three parameters are the inputs and the next two parameters are the outputs. So we have full adder 1, the name of the component, full adder, port map, A1, B1, C1 with outputs S of 1, comma C2. Include the signal C2 here. We continue doing this. So full adder 2 would be full adder, port map, A2, B of 2, C2, and then you have S of 2 and C3. Similarly, for the final full adder, you have port map, A3, B3, C3, S3, and let's say you have C out. So let me put down the signals, C3 and C out, and end. So this is structural programming. Make the components, test the components, write the main entity or the main interface, declare the components, and call the components with the correct port maps. Now with port mapping, you need to be careful because if you interchange these positions here, so instead of S of 0, you write C1, and instead of C1, you write S of 0, your whole equation is going to change because that's how your half adder works. So your half adder is having two inputs, X and Y. The first output is S and the second output is C out. Now remember, if you interchange them, it's going to be totally different here. So instead of S, if you write C out, and if instead of C out you write S, it's going to be different. So the order of the parameters are pretty important in structural programming. This is something that you need to be really careful about.